good to be here. We're actually very excited about being here today because I'm sure Scott will agree, but it feels like we've been working on these series for 5 or 6 years now because much of the content from the Australian curriculum version 9 was developed into the Western Australian curriculum. The resources for New South Wales, I know were considered by the authorities for the Western Australian curriculum. Spent 3 or 4 years on the diagnostic tool. So we're very excited to get to this point where we can talk about the Western Australian curriculum, which we love, and some of the great ideas that have come in, and not just things that have come from the Australian curriculum version 9. So we'll talk a little bit about the Australian curriculum, but more importantly, what the Western Australian curriculum has done with version 9. We'll look at the structural changes, some of the new content. We'll talk about the optional content in the Western Australian curriculum, the modelling and digital technologies, substrands, the Cambridge resources, and of course the diagnostic tool as well. So let's just briefly run through the overall changes for the Western Australian curriculum. I'm sure many of you know of these things. We'll just mention it now. So implementation due for next year. The curriculum is based off Australian Curriculum 8.1, not one of the other versions following 8.1, but much of the work that went into version 9.0 of the Australian curriculum has been included for Western Australia. And we know that New South Wales curriculum, with all their examples and so on, were considered as well as part of the curriculum here. The strands and substrands have been retained. So 3 major substrands has been retained, unlike the Australian curriculum, which split them into 6. And so Western Australia has retained the 3 main strands and then updated and reorganised all the substrands, which are no longer in the Australian curriculum. So that structure that people are used to is still there, along with the proficiency strands, understanding, fluency, problem solving and reasoning have been retained as well. You can see by looking at the contents of the Western Australian curriculum how the 3 major strands and the substrands are really forming the structure of the whole curriculum. And you'll notice a couple of new ones in there. Does anyone want to participate and tell us which ones are different compared to the old curriculum? Yep. Right, financial maths is a whole new substrand all the way through. Any others? And the modelling as well.
Do we have an activity, David?
We might have an activity shortly, actually, and if people want to begin preparing for that, you'll find a little white workshop booklet, which we'll work through in a minute. You can see some of these changes. If you dive down into the curriculum, you'll see as you work through the substrands, this one's called algebraic techniques, you can see how the curriculum is structured with the substrands and their content descriptors, and also with the examples now. Examples are there for every content descriptor, and this is something that we picked up from New South Wales, but I think will be very popular in Western Australia as well. So it's true that 10A label's gone and we now have optional in Western Australia. Same with Australian curriculum, they've gone with the optional word as well. Optional content now for year 9 and 10, this is unique to Western Australia and has been very well received. So this is true. New financial maths is obviously true. Networks in year 10, if you said true, you've probably been reading too much of the Australian curriculum. It's actually false over here. But it is something that Cambridge will make available for anyone who would like to teach that in year 10. So false for that one. Time zones is expanded into year 7 from year 8. This is true for Western Australia. It's a really nice move because it spreads that curriculum content out very nicely. Triangular prisms, bit of a trick question, number 6. It's actually false. True for AC, but false for WA. Same for 3D coordinate systems. Cleverly, WA did not put that in year 8. Similar figures, false, that's introduced more at years 9 and 10 to Western Australia, whereas some of you might be used to teaching a bit of that at year 8. Cambridge have retained some of these things as extending sections in year 8, but in terms of the core curriculum, that's false. It's in 9 and 10. Same with introduction to circles, pi and circumference. This is an Australian curriculum idea in version 9, but not picked up in WA. That's left as it was, with most of that work being introduced in years 8. Oops, sorry. Okay, number 10, unit circle is introduced at year 10. What do you think? Well, it's actually false, but it's true in that it's actually in year 9 optional. Arguably the most interesting inclusion in WA curriculum, introduction to unit circle at year 9. So that statement is false because it's in year 9. Pythagoras moved to year 8, yes. Inequalities with equations introduced at year 9, no. If you read the curriculum, there's really a proper introduction there at year 10. I'm not talking about inequalities in general, but inequalities actually solving the equations. All right, number 12 the same. Number 13, stronger emphasis on ratio and proportion. This is true. This is very much a feature of the Australian curriculum, and many teachers wanted more on ratio and proportion at year 10, and that's come through in Western Australia as well. Polynomials used to be 10A, so has that shifted across to optional year 10? No, it's gone from WA. Retained at Cambridge to some degree, but not in WA. Parallelograms introduced at year 8, true. Venn diagrams, this is unique to WA. Venn diagrams introduced at year 7. Australian curriculum has that at year 8. Here's a controversial one. Units of volume conversion. So conversions of units of volume. False. I had to change that one because it was true before the final version came out. So the draft had that in there for WA, and then they moved it back out to match the Australian curriculum so that it's introduced at year 8. Laws for logarithms, is that in 10 optional? No, that's gone. The optional for AC still. Combinatorics, that's advanced counting techniques, is that optional? No. That's something that other states are thinking about. Errors, accuracy, and so on, yes. More in AC, more in WA. The sine rule, cosine rule, area rules for triangles, they are now optional for WA in year 10, and I believe they're still optional for Australian curriculum. Modelling, number 22, clearly that's in, along with digital tools and technology are embedded throughout the curriculum. Looking at the financial changes, you can see here the sub-strand financial maths is developed clearly right across 7 to 10. So transactional statements and financial records at year 7, forms of payment, fees, interest at year 8. 9 has income, superannuation and tax, and more on tax tables and compound interest at year 10. Modelling, we know now, is embedded right through and has its own substrand for each of the 3 main strands. Number and algebra is 1, measurement and geometry there's 1, and also for probability and statistics. So with plenty of development around the country, and in particular, much work done in Queensland with modelling and with the Australian curriculum, the authorities in WA have extended this research and have decided to make it explicit that this should be taught across the curriculum. A common language has been developed with words like analyse, represent, solve, determine, interpret, communicate, and so on. And these are explicitly mentioned throughout the curriculum. You may not be able to read this, but you can see these words appearing in the content descriptors for Western Australia. The keywords are there, and you can see the horizontal development. Each of the content descriptors start with in real-world situations involving whole numbers, positive fractions, and then they are expected to be able to analyse, interpret, represent, and communicate. Now, I have an example of a potential modelling task, which is also being printed into your booklet. And this key modelling task is one from Year 10, Cambridge, that I've selected, and we'll just do a small activity on this in a minute. But a modelling task is essentially a problem where mathematics is used to describe the problem and explore and come up with a solution. So a context is provided, and a preliminary task is a low-level or low-floor context building activity to strengthen both mathematical readiness and contextual understanding without preempting the modelling strategies. So this particular modelling task asks students to think about an impassable object like a gorge or a river or a road, something that they would like to find the distance across without actually going into that area. So with this preliminary task, students are asked to place pebbles or find trees and measure the distances between them in such a way that they're lined up as two triangles. And I'm pretty sure everyone knows which area of mathematics this relates to. But working through that, they'll be able to build their understanding of similar triangles and think about the mathematics that they might use in a modelling context. Then when they get to the actual task, they're required to choose an object, like a road or a river or a ravine that they can get to, and then consider, as part of the modelling process where they're analysing and representing, is where they're going to consider possible placements of the pebbles or rocks or trees or whatever it might be to create the two similar triangles, and then take the measurements. So they're modelling the situation and they're drawing diagrams, taking measurements, and creating something that they might be able to use mathematics with. Then, to solve, they would prove and confirm that the triangles are similar, determine a scale factor, and then solve the problem by using that scale factor to determine or estimate the river, the distance across the river or the ravine. Now, I actually did this activity with my Year 10s only last week, and they coped quite well with that. But when we got to interpret and verify, I could tell that there was an added challenge to this, because interpreting and then verifying in this modelling situation could mean that they rearrange their pebbles for the same situation, have different measurements, but hopefully come up with very similar answers to the distance across. And that was a really big step for many students in my class, realising that it didn't matter how they originally placed the pebbles, provided they created similar triangles, they could confirm the distance across the road or the driveway or whatever they chose. So the interpretation and the verification was a fairly complex part of this modelling activity. And to finish, they had to write all that up and communicate that in a report. Something that was readable, cohesive, and had all the solutions and diagrams, and a photo as well of their activities. There are some extension questions there as well. But let's do a little bit of modelling ourselves on that activity. So what would be the most common error a student would make when trying to prove that those triangles are similar? What would the error be? Yeah, thinking it's RHS because there's a right angle there. But there's only one pair of corresponding sides. So RHS needs 2, and all the other ones need 2 as well. So there are, obviously we have vertically opposite angles and a couple of corresponding angles as well. So AA, AAA is the proof that that particular example is from one of the chapters at year 10, and we'll talk a little bit about modelling later when we talk about some of the new resources that Cambridge are going to offer. So modelling is in the curriculum, and it's something that we've tried to focus on at Cambridge for a number of years now. Let's talk about the optional content for 9 and 10. So the extension pathways are now developed formally right through for 9 and 10. And this is welcomed at Cambridge because the Cambridge series always included extension pathways through 7, 8, 9 and 10. So the Western Australian curriculum is beautifully aligned with what we were doing at Cambridge in the first place. Much of the old 10A and some of the more advanced Year 9 content is rebadged now as 10A. But some of the old 10A has been removed altogether, like log laws, factor theorem, remainder theorem for polynomials, and so on. We mentioned that earlier. So it's great to see this pathway now formally recognised through Years 9 and 10. We have some shifted content. Let's see, Australian time zones are now developed through Year 7 and international time zones at Year 8. So this is a really good way of developing content through, as an example. Angle sum of the quadrilateral has moved from Year 8 to 9. We've got a strengthening of algebra at Year 9, both in core and in optional. Pythagoras moved from Years 9 and introduced at Year 8. We have content which is new. We've mentioned some of these before. So the financial maths, Venn diagrams, Australian time zones, Year 7, more on proportion and ratios at Year 7 as well. I won't spend too much time on this because we've mentioned it before, but yeah, Pythagoras is in Year 8. Two-step experiments is in Year 8. Introduction to gradients and straight lines is new at Year 8. More on 3D solids. Not coordinates, but solids. At Year 9, income and taxation. Unit circle is there, but optional. There's more work in 9 and 10 on errors, accumulation of errors, and accuracy. This is now something that's very clear, not just in AC, but more so in Western Australia, and more on data types and sampling, thinking about bias and those types of things. In Year 10, regions in the plane, financial maths, logarithmic scales, not laws, more on measurement with scaling, two-way tables, all these types of things. Solving trig equations is in the optional components as well. But it looks like there's a fair bit that's new, but many of these things I think teachers were already doing as part of their previous work or doing optional or extending material before anyway. So what are we offering at Cambridge and how have we dealt with all these changes? One of the key changes at Year 7 is the combining of the 2 old geometry chapters into one. And that way we now have 10 chapters in every book right through from 7 through to 10. And this, I think, will make it easier for teachers to work through the content. All the transactional statements at Year 7, Venn diagrams and those other things that I mentioned have all been included in the Year 7 book. So Year 8, similar chapter structure that you might have seen before with an array of updates over the years, but all the new content included as well, like more on 3D solids, Pythagoras. Well, Pythagoras was already there as an extending section, or 3 actually, but it's there as the core material now. Year 9 includes the work on unit circle, errors and accuracy, income and taxation, all those things are in there. There's more of a change in the way we've structured Year 10 because there was more of a significant change with the Western Australian curriculum at Year 10 and certainly the Australian curriculum, which was an influence. So with the changes, especially with some of the 10A content leaving, it made sense for us to restructure some of the sections in Year 10. One of the key ones was the introduction of more financial maths and more logarithm work. And so it made sense for us to create a chapter number 3, financial maths, exponentials and logarithms. It worked really well. And a lot of the optional and extending sections on functions and polynomials and so on came together quite nicely as a chapter 10. No longer being interrupted by log laws. At Cambridge, we have retained some of our classifications where any section in the series that is considered revision or significant revision of previous year's work is classified as consolidating. Anything that is considered or matches the optional content obviously has the optional, and other sections which go beyond the Western Australian curriculum but are logical extensions at that year level and are not optional are called extending. So 3 special classifications. All the sections which do not have a red classification are obviously core to Western Australia. So that level of differentiation or creating pathways at your school can be helped greatly by you knowing which is revision, which is core, which is optional, and which is beyond that at that year level. There are other extensions which you might be interested in being offered by Cambridge as well. So because the Australian curriculum is looking at an area of triangular prisms at year 7, the authors and the team at Cambridge felt that we would like to keep that there in the Western Australian curriculum book and call it extending. It fits very well, and there may be some schools that have the time and the space to be able to do those. So that would be an extending section that's beyond the curriculum. The algebra of polynomials at year 10, we talked before how that's gone, but we still make that available. Simultaneous equations at year 9, that is beyond core and optional at year 9, but it's a logical extension for many schools, and so we've retained that in the books throughout the series. So that's all the extending sections that I'm talking about. Beyond that, there are digital-only mini chapters, if you like, that other states are enjoying. For example, combinatorics, advanced counting techniques, the work on networks I mentioned before. There are some Cambridge sections on rates of change, the laws for logarithms. They're quite significant pieces of work, and many teachers would have used some of these sections in the past, and they've been redeveloped and they'll be available as digital chapters for Western Australia, along with the algorithmic thinking chapters. Now, in terms of the features at Cambridge that we have retained, we have retained a structure in the exercises that many of you would be familiar with the division of the questions based on the proficiency strands. There has been a lot of work over the last couple of years, especially with those early questions in each exercise, where we wanted to make sure there was a one-to-one match of the first couple of questions with the examples. So a while ago now, we moved the building understanding questions to the teaching area of the chapter. And so those first few questions have a one-to-one relationship with the easier examples in the textbook. So we retain the structure and we retain the differentiated learning pathways through the series, with the easiest selection of problems on the left, standard in the middle, and the more challenging selection of problems on the right-hand side, where students are picking up the more challenging problem solving and reasoning questions, and also the enrichment question in each section. We retain the learning intentions. These have been refined for the new editions, as well as the success criteria with their examples at the end of each chapter. As well as that, of course, we retain other features that people are used to, the progress quiz, situated about halfway through the chapter, which is in the print book, but it's also available as a printout or an auto-marked quiz. And also one of the things that people like are the Now You Tries, which are mirror images, if you like, of the examples after every example. So teachers were working through the examples with their students, and now they have something else that they can offer their students, where the answers now are available in the print book because people wanted them there. Is that correct, Scott?
In the back of the book.
Yeah.
That's right. Yeah.
So the answers to those are in the book. And a similar section structure with the learning intentions at the beginning for teachers to use, the introduction and the lesson starter activity that some people might like to use, the comprehensive but concise key ideas, and then the building understanding questions have been redesigned as more of a teaching tool rather than the start of the exercise. And this helps connect with the prior knowledge and help teachers transition to new concepts and methods for that section. Of course, we retain the examples and the Now You Try. Every example has a video to match on the digital. We start with the fluency questions. And as I said, we wanted to be sure that the majority of students who tackle the questions at the beginning were able to do this without necessarily putting their hand up. So the correlation between the first few questions and the examples is almost one-to-one. You can see how the three pathways are working through the different proficiency strands. So even the left side, the weaker students, they're still getting some problem-solving questions. Sure, they might be a bit easier, but they might be classified as problem-solving or reasoning, for example, rather than fluency. The reasoning questions and enrichment questions are on this page, and the enrichment is yet another opportunity for teachers to help differentiate at the top end and extend students' knowledge in that content area. Other things we retain are the applications and problem-solving questions, positioned about 2/3 of the way through the chapter. And these are extended response type questions that link with similar types of experiences that students might have at year 11 and 12. The mind map, the problem solving and challenges pages, and the chapter reviews, all those things are retained and are expected. I mentioned the modelling before, and while we created some of these modelling activities for Queensland and with the research that they've done, and also for the Australian Curriculum Series, these have been adapted for the Western Australian curriculum with the correct language used as recommended, using words like analyse, represent, solve, interpret, verify, and communicate. Not be able to read this, but this is another example where students are modelling a cylindrical park seat where there's a fixed amount of concrete and they're looking at this surface area and how much space is going to be painted, and looking at the relationship between the radius and the height and considering how much surface area there is if they change that relationship on the fixed volume. Just talking about modelling a little bit more, you can see that that modelling task is set up in a certain way. It's been written so there's a realistic chance that even if a teacher did not prepare for the lesson, there's a chance that it could be successful. So there's that warm-up preliminary task, and there's a reasonably highly scaffolded modelling task and some extension questions. But we also understand that there are other ways of thinking about modelling. And so one of the tasks that we've added to the list is a re-engineered modelling task for Western Australia, where we still have the preliminary task, but there's a new section called Working with Models. And in this section, we're explicitly aligning with the WA's modelling phases, providing clear metacognitive clues where students are engaged with partially constructed models or build them step by step. Now you'll find an example of what we've done on the next page of your booklet, where you can see one of the Year 7 modelling tasks has been re-engineered with these new sections. The preliminary task is still there, but the next section, working with models, takes those key words from the Western Australian curriculum, and we ask students very specifically to do these things, to think about what is happening with the modelling process in this particular context. Following that, there's a very clear scaffolded modelling task. And then at the end, a similar task that is completely unscaffolded. So this is more open-ended and unscaffolded. And we believe this is somewhat similar to what might be in the text as an experience, but offers an alternative to modelling tasks for teachers and their students. Scott, were there any other motivations for recreating some of the modelling tasks in this way?
Yeah, so there is a variety of views about how to teach modelling, especially at the younger levels. Now, you may teach year 11 and 12 courses and would be familiar with the mathematical thinking process and the statistical investigation process and the language that is used or expected by SCASA in a successful student response, and the ability to recognize that there are simplification is necessary as part of the modeling, mathematical modeling of the real world. And hence there are assumptions that are made and students need to be aware of those assumptions. Think about the technology that they're using, all of these different things. And there are challenges with perhaps reflecting those expectations at the younger year level. So the activity that you're looking at there is for year 7, but it still allows for some fairly explicit discussion of the fact that there are assumptions and what are assumptions and all those kinds of things, even going back to year 7. So SCASA is very keen to see the steps of the modelling cycle taught explicitly to your students, even going back to year 7. So we have developed these additional activities. They'll be available in the teacher resources to download. Rubrics will be provided, all of these kinds of things that reflect the kind of language that's not only in the WA curriculum, but also in the mathematical thinking tasks, the exemplars that SCASA provide at year 11 and 12, to allow those discussions to get your students used to seeing activities that are like this, so that by the time they get to year 11, that they should be fairly familiar with this kind of mathematics.
There are 10 modelling activities for every series. So there's one for every chapter. Now, one may not expect to get through 10 modelling activities in a year, because you might be doing other things as well. But a modelling activity has been written for every single chapter right across the series. So that's 40 of them in the Cambridge 7 to 10 series. There are also another 40 activities which come under the Digital Tools and Computational Thinking banner, which is new to the series. And the WA curriculum has clearly tried to modernise the curriculum and include words like digital tools, 32 times, in fact, if you count them. This connects well to the current technologies and modern applications in mathematics and computational thinking. And you can see that definition there, that computational thinking is a way of solving problems that involves breaking them down to smaller parts and identifying patterns and developing step-by-step instructions. And this has strong connections with the new Australian curriculum and what's been going on in Victoria, for example, as well. And so there is a recognition around the country that many of the problems that we are solving in industry these days are solved not necessarily with Euclidean geometry or algebra skills, but they're solved computationally, where potentially an algorithm is being used, or technology is being used in such a way to find a solution where algebra is not being used, where problems are so complex that we zoom into the answer rather than trying to solve it exactly. And this is reflected in many of the world's competitions, including over here in WA, which probably has some of the best students in the country with the computational and algorithmic thinking competition run by the Australian Maths Trust, and the informatics competition, which are very quickly becoming more popular than mathematics competitions. And this has been recognised around the country, in the Australian curriculum, in other countries as well. And so problems that can be solved computationally are starting to appear in the mathematics curriculum. And so to react to that, we have written 40 investigations connecting to the content of each of the chapters.
Maybe we could do for 30 seconds, maybe you could talk to the person next to you and have a discussion about whether computational thinking is or is not in the WA curriculum. What do we think? Yes or no? What's the answer, David?
I think both.
Yes.
Both would be the answer, because the word algorithm and the word computation is perhaps not there, but there's clearly an understanding that it exists, and this is an influence. And the word digital tools comes in so often that I believe the curriculum is encouraging us to start to think this way. So using technology, using spreadsheets, graphing calculators, finding numerical solutions, doing simulations in statistics and probability, this all fits under the banner of computational thinking. And I think a lot of us have always been doing it. Like when we use the bisection method to solve an equation, for example, at year 11 or year 12, or we are finding an intersection point using graphing software, not an algebraic solution, is essentially solving a problem numerically. And so this is something that is creeping into our curriculum, and we're hoping that people will enjoy the computational and digital tool activities that we have in every one of the chapters. In fact, we have a little activity now, and this is in your booklet as well. We've just printed one off from year 7. It's called Soccer in the Rain. And this is one of our digital tools and computational thinking activities. And we're going to do this now using a spreadsheet. So let me just talk a little bit about what the activity is. So what we have is, from previous year data, we know over the past 100 or so matches, 20 of them were cancelled due to rain. So based on previous statistics, a match is cancelled about 20% of the time. So what we're going to do is, without too much complex maths or binomial distribution or whatever it might be from year 11, year 12, we're just going to simulate this situation using technology. So there's a bit of work in the getting started activity. Just like in the modelling, there's always a bit of a getting started activity to warm students up to what the mathematics is. But when we're using digital tools, a great way to simulate this would be to use a spreadsheet. So we're not talking about programming or writing a little Python code or anything like that. We can do this with a spreadsheet. Okay, so we've simulated running 20 seasons. Now, the question in the activity is, what's the chance that a soccer player will go to the season and play at least 7 matches where it's dry and not being cancelled by wet weather? So we have 20 simulations now, and looking at your table, let's see, if we want to be playing, we need it to be dry, so we need it to be 3 wet days or less, guarantees 7 or more times when it won't be cancelled. So how many of yours were 3 or less for wet? How many? 16 out of 20. Right, so 16 out of the 20 were dry. Yeah, 16 out of the 20 means that were at least 7 matches being played. So that is an estimate of the probability that we'll be playing at least 7 matches in a season. Now, for those people who are more advanced with their probability, you'll probably know that this is a binomial distribution. But by using simulation and a very simple little bit of Excel code, we're using computational thinking. We're introducing students to these ideas, and we're using technology to solve problems like this without necessarily going to a really high level of maths. A couple of other things which I would like to mention is, just very quickly, all those investigations we've talked about come with rubrics, which can be used as a guide. Another feature that we quite like are our skill sheets. So we were finding that teachers were still wanting a very simple skill sheet, 1 per lesson for their lessons. Maybe as an opening quiz or an exit ticket or a little piece of homework that didn't go over more than 1 page of work and aligned very strongly with the key skills and success criteria for that section. So that's a skill sheet for every activity. And PowerPoint slides. Another thing teachers were doing is they were creating their own PowerPoints and snipping bits and pieces out of the Cambridge resources. So Cambridge decided to do this for everybody and have created a PowerPoint for every lesson where all the lesson material from the learning intentions through the key ideas and the examples are all presented as a PowerPoint presentation. And probably won't have time to do this now, but the examples are presented where teachers have control on when the solution is being presented in front of the students and when the now you try comes up. So students can then try that and when the answer to that comes up as well. So PowerPoint presentations for every section. A number of investigations.
I was just going to say, David, that's about 100 of those PowerPoints per title and about 400 from 7 to 10. So as David says, one per lesson, and you can modify them. You know, they're all editable if you'd like to.